Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. Before I get into the fourth and final segment on women in engineering, I have a small announcement. As I've said before, I love making this podcast. But between my stressful engineering job, the podcast, and all of the other things going on in my life, I'm exhausted and I'm starting to burn out. I keep saying, I just need to get to this date or that date and it will lighten up. But that doesn't seem to be the case. I've read that most podcasts don't make it past 7 episodes, so the fact that I've made it to 20 in itself is a huge feat. I'm incredibly proud of what I've been able to accomplish in these 5 short months, and I want to keep bringing you the engineering failures you love to hear about. So going forward, I'll be releasing Failurology episodes bi-weekly. I had hoped to maintain weekly episode releases, but it's just not sustainable long term. I hope you understand, and if you want to talk about it, you know where to find me. So far on the Women in Engineering segments, I've talked about the limiting factors, what we can do as a community to build a more inclusive industry, and provide resources to improve recruitment, retention, and professional development. This week, on the fourth and final segment of Women in Engineering, I'm going to tell you a story about a woman named Elsie MacGill. Born in Vancouver on March 27, 1905, her father was a prominent lawyer and her mother a judge. Elsie's mother and grandmother were active in public service and worked in the suffrage movement. Later in life, she would write a book on their life and spent much of the 1960s working on women's rights. She was quoted as saying, "I have received many engineering awards, but I hope I will also be remembered as an advocate for the rights of women and children." She received a rigorous education as a child that allowed her to enter the University of British Columbia's Applied Sciences program when she was just 16, although the Dean of Faculty asked her to leave after one term. Despite contracting polio in the mid-1920s and learning to walk supported by 2 strong metal canes, Elsie graduated with a Bachelor's of Applied Science in Electrical Engineering from the University of Toronto in 1927. And then she received her Master's of Science in Engineering Aeronautics from the University of Michigan in 1929. She was the first woman in North America, and likely the world, to do so. When I went to school, I was one of 3 women out of 60 total students within the mechanical discipline, and the only female in the automotive engineering specialty. So I kinda get it. She then attended doctoral studies at MIT in Cambridge from 1932 to 1934. Elsie went on to become Chief Aeronautical Engineer at Canadian Car and Foundry, which is now Bombardier. She was the first woman in the world to hold this type of position. Under her leadership, the factory expanded from 500 workers to 4,500 by the end of World War II. Half of them were women. She was responsible for streamlining operations on the production line and providing design solutions to allow aircraft operation during winter, by developing de-icing controls and fitting the planes with skis to land on snow. After the war, Elsie moved to Toronto to set up an aeronautical consulting business. In 1940, she was quoted saying, "My presence in the University of Toronto's engineering classes in 1923 certainly turned a few heads. Although I never learned to fly myself, I accompanied the pilots on all test flights, even the dangerous first flight, of any aircraft I worked on." In 1946, she became the first woman to serve as technical advisor for the International Civil Aviation Organization and helped draft the International Airworthiness Regulations for design and production of commercial aircraft. In 1947, she was named the chairman of the UN Stress Analysis Committee, the first woman to chair a UN committee. From 1962 to 1964, she was the president of the Canadian Federation of Business and Professional Women's Club. And in 1967, she was named to the Royal Commission on the Status of Women in Canada. Sadly, she died on November 4, 1980, after a short illness. She received a number of posthumous awards, such as the Society of Women in Engineers U.S. Achievement Award, the Centennial Medal by the Canadian Government, the Order of Canada, the Amelia Earhart Medal, the Ontario Association of Professional Engineers Gold Medal, as well as being inducted into both the Canadian Aviation Hall of Fame and the Canadian Science and Engineering Hall of Fame. Due to our current pandemic, I've been thinking more about what was going on in the world in the early 1900s, when the last global pandemic occurred. Elsie would have experienced 2 world wars, a global pandemic caused by the Spanish flu, and the Great Depression, all before she was 50. That's like 4 lifetimes in one. And she still accomplished so many things. If I'm able to do half of the things she did, I will have a very successful career. She is unbelievably inspiring. Now, I did say this is the 4th and final segment on women in engineering, but I meant final as in this series. This will not be the last you hear from me on women in engineering. I'm working on some other projects, so stay tuned for more. Let's get into the episode. Now on to this week's episode. Every 10th episode, I'm going to cover an engineering marvel. Something a little different to mix things up. But even engineering marvels aren't built without problems. The more complex the design, the more there is to go wrong. This week's marvel covers 2 of my favorite things: engineering and tunnels. It's the Channel Tunnel, or more commonly known as the Eurotunnel or the Chunnel. The Chunnel is a 50-kilometer international rail tunnel connecting England and France under the Strait of Dover, which connects the English Channel to the North Sea. It's the 13th longest tunnel in use. It's also the 4th longest rail tunnel, has the longest undersea tunnel section, and is the longest international tunnel in the world. In 1994, the American Society of Civil Engineers named the Chunnel one of the 7 wonders of the modern world. Also on that list are the Empire State Building, the Itaipu Dam, the CN Tower, the Panama Canal, the Golden Gate Bridge, and the Delta and Zuiderzee Works, which are a series of dams in the Netherlands. Proposals for the tunnel started as early as 1902. One included an artificial island halfway across for changing horses. In 1984, 4 serious proposals were discussed, and they are as follows: a 35-kilometer suspension bridge with 5-kilometer spans and a roadway that would be enclosed in a tube, a 21-kilometer tunnel between artificial islands approached by bridges, large-diameter road tunnels with mid-channel ventilation towers, although this option had concerns with ventilation, accident management, and driver mesmerization. And then, of course, there's the Channel Tunnel, which is a rail tunnel. In the end, it was chosen because it offered the least disruption to the shipping channel, the least environmental disruption, it was the best protected against terrorism, and the most likely to attract sufficient private financing. The tunnel was constructed from 1988 to 1994, and it cost almost €5 billion to build at the time, which was equivalent to about €12 billion today. It cost 80% more than expected, which projects like this often do. The project employed 13,000 people at the height of construction. Unfortunately, 10 workers, 8 of whom were British, were killed during construction. The average depth of the tunnel is 50 meters below the seabed, with the deepest section being 75 meters below. The tunnel is actually 3 tunnels, 2 for trains, which serve both passenger and cargo, and 1 tunnel for service and emergencies. The rail tunnels are 7.6 meters in diameter and spaced 30 meters apart, with a 4.8 meter diameter service tunnel in between. The rail tunnels are connected to the service tunnel every 250 meters by a 2 meter diameter duct that doubles as a piston relief. As the train rushes through the tunnel, it pushes the air forward, just like a piston in an engine, although the train is not necessarily sealed to the tunnel like a piston is to a cylinder. This is referred to as piston effect, and it impacts passenger comfort, ventilation systems, tunnel doors, fans, and the structure of the trains. The piston relief ducts provide the displaced air somewhere to go, rather than continuing to push forward down the tunnel, building pressure. However, unexpectedly, the relief ducts create a lateral force on the side of the trains, which is why the speed is reduced to 160 kilometers per hour, even though the trains and tracks are rated for 200. There are plumbing, ventilation, and cooling plants on either end of the tunnel. They are both designed to provide 100% service in the event that one side should fail. Of course, I'm going to cover the mechanical systems first, but it's not my fault. I eat, sleep, and breathe mechanical systems. They are the parts I find most fascinating. If you had told me when I was a teenager that I would get this excited about tunnel HVAC, I would never have believed you. But here we are. The ventilation system maintains a higher pressure in the service tunnel than in the rail tunnels. This prevents smoke from seeping into the service tunnel or from crossing from one rail tunnel to the other via the service tunnel in the event of a fire, allowing rescue crews to reach and evacuate passengers safely. The average temperature in the tunnel is around 25 degrees Celsius. Interestingly enough, I had expected the tunnel to be cold. After all, it's dark, humid, and underground. But the friction of the train wheels against the track and the trains themselves generate a lot of heat that must be addressed. Actually 6,000 tons to be exact. For reference, a 30-story condo tower in Calgary requires about 200 tons of cooling, so the tunnel needs about 30 times that. Fun fact, cooling is not the addition of cold, it's the absence of heat. You might be thinking, well, Nicole, that's the same thing, but it's not. To cool the tunnel, or make it less hot if you will, cold water is circulated through a series of 600mm diameter distribution pipes which absorb the heat from the tunnel. The heat is then rejected to the atmosphere at the cooling plant on either side of the tunnel. The original cooling plant for the tunnel consisted of 4 2,000-ton chillers on the English side and 4 1,700-ton chillers on the French side. The original chillers used R22 refrigerant as their cooling medium, which has since been phased out and is no longer available due to environmental concerns. In 2016, rather than retrofit the refrigerant, it was decided to replace the chillers after 22 years of service. The new chillers use R1232ZD refrigerant with improved efficiencies. Seawater air conditioning is also a cooling option that is even more energy efficient. A project related to seawater cooling began in mid-2020 and is expected to be completed in 2023. What about water? The tunnel creates essentially a bowl. You can't exactly use gravity to drain water out the ends of the tunnel when the middle is at a lower elevation. So any water that collects from rain or groundwater seepage is collected and pumped out using various pumping stations. How does one build a tunnel exactly? Well, you could try to stop the water, dig the hole, and lay the tunnel down. Sounds crazy though, right? What they do is they drill or bore horizontally under the seabed and infill the tunnel walls, which were designed to last 120 years, behind the boring machine. To speed up the process, they actually bored from the English and French side at the same time. And miraculously, they were only offset by 36.2 centimeters by the time they met about 2 years into the project. Although technically not a miracle, they don't just start drilling and hope for the best. There are geological surveyors on site that measure the placement and trajectory of the tunnel throughout the process to keep it on track. They do similar measures when building a tower to make sure it stays vertically plumb. We don't need any more leaning towers of Pisa. The service tunnel was drilled as the pilot tunnel and progressed about 30 meters ahead of the rail tunnels, the sacrificial lamb, if you will. As I mentioned, the tunnel was drilled on both sides at the same time. About 20 years of geological surveys had confirmed that they could tunnel through what is called the chalk marl stratum layer. There's a geological section on the website page for this episode, link in show notes, that shows the buildup of the earthen layers under the water. The chalk layer was ideal for drilling because it was made up of 30 to 40% clay, making it impermeable to groundwater, but still relatively easy to excavate. I'm currently working on a project on Vancouver Island that is constructed on clay. The clay pretty much tanks the underground parking level, and any rainwater that lands on the surface of the clay just stays there in pools and doesn't drain away. Honestly, it's a mess. It wasn't all sunshines and rainbows drilling the tunnel. There's a 5-kilometer section on the French side that was not clay and was more challenging to drill through, so the British were able to drill further than the French, and when the two tunnels met, it was past the halfway mark. In addition, the chalk layer was not at uniform depths, and so the tunnel has a few ups and downs to stay within this layer. 11 boring machines were used to build the tunnel, each as long as 2 football pitches, or as we call it in Canada, soccer, with the tunnel walls being infilled behind. The train tracks are low vibration, free-floating rails that are held in place by gravity and friction. The Sunnyvale International Corporation's Low Vibration Track System, or LVT, was chosen due to its reliability and cost effectiveness. I'm used to seeing rails being laid on a bed of gravel, but that's not the case in the Channel Tunnel. The LVT system consists of patented individual rail supports with a concrete block and rubber isolation both where the rail contacts the block and where the block contacts the tunnel. This reduces the amount of vibration that's transferred from the train to the rails and the rails to the tunnel. The average travel time from one end of the tunnel to the other is 35 minutes. The train consists of main cars totaling 775 meters in combined length, the equivalent of 8 football or soccer pitches. Roughly 60,000 passengers, 4,600 trucks, 140 coaches, and 7,300 cars pass through the tunnel every day, representing 26% of total trade between the UK and continental Europe, or at least it did pre-COVID. I'm sure the lockdowns have impacted this considerably. The trains are electric. If they had been powered with another fuel such as coal or diesel, the same ventilation concerns they had with cars would have existed, and significantly more ventilation would have been required. As mentioned earlier, the trains are limited to 160 km per hour operating speed, even though 200 km per hour is possible with the trains and rail construction. The electricity is provided to the trains overhead, similar to electric buses or trains in cities. And there are 2 electric substations, one on either end, to deliver power and lighting to the tunnel. As I said at the top of the episode, engineering marvels are not without problems, and the tunnel is not exempt. Fire safety was a critical component during design. It has to be. You're potentially trapping people 25 kilometers underground if an accident were to occur halfway. The passenger cars have been designed to withstand a fire inside for 30 minutes, with a transit time of the fire brigade being 27 minutes. Now, I don't think the entire car disintegrates after 30 minutes. I think the fire is able to penetrate the wall in isolated locations where the fire is strongest after 30 minutes. But a 3-minute buffer for the fire brigade seems a little light to me. To combat this, 2 service vehicles with firefighting pods are on duty at all times with a maximum delay of 10 minutes to reach any point in the tunnel. And the cars are equipped with fire detection and halon gas extinguishing systems to limit the spread of fire without flooding the tunnel in water. And if it comes to it, there's a 250mm water main in the service tunnel, which can provide water in 125-meter intervals to the rail tunnels to be used if needed. The ventilation system I talked about earlier also can be used to control the movement of smoke by moving air and smoke in one direction through the tunnel. Let's say a fire broke out 10 kilometers in from the British side. The ventilation fans could direct smoke towards the French tunnel inlet, assuming it wasn't occupied by another train, allowing the emergency crews to safely enter from the British end without being blinded or suffocated with smoke. Even with all the preventative planning, there have still been a few fires, some of which led to extensive damage. In 1996, a fire damaged 500 meters of the tunnel and affected operations for 6 months. While the fire itself probably impacted no more than 50 meters of the tunnel, smoke is a real pain. I worked on a new building several years ago that was the victim of arson right before occupancy. Someone lit a stack of pallets on fire at the base of the parking entry ramp. It only set off a couple sprinkler heads in a mostly concrete area, but the smoke from the fire got into the ductwork. By the way, in the movies, when someone sets off a sprinkler head with a lighter and all of the nearby heads go off, that is a myth. Unless you are dealing with a special system, only the heads closest to the fire are set off. Sprinkler heads contain a small device that melts at a specific temperature. When that melts from the heat of the fire, the stopper in the head drops and water comes spraying out. So on that building that had the fire, the HVAC system design contains central heat recovery units, which means that all of the exhausted air from the building is collected and travels through a heat wheel before it leaves. This warms up the cold incoming air, so less energy is needed to heat it. While this is a really cool energy-conscious system, it means that all of the supply ductwork was connected and all of the exhaust ductwork was connected, and both were lined with acoustic insulation. Once smoke got into one section of duct, it was easy for it to travel through the system and impact the entire building. The amount of smoke damage to the ductwork lining, as well as the electrical and controls components throughout the building, was extensive. And even though we were only about a month away from occupancy at the time of the fire, The building completion was delayed a full year to address all of the smoke damage. Back to the Chunnel. On December 18, 2009, 5 Eurostar trains broke down, leading to roughly 2,000 passengers being trapped in the tunnel for 16 hours without power and some without food or water. The fact that 5 trains broke down at once was seen as unprecedented, and as such had not been adequately planned for. You want to know what happened, don't you? I sure did. Thankfully, an investigation was done and the report was made public. Isn't the internet the greatest? On December 18th, there was heavy snow in England and France, up to 40 centimeters and temperatures of -4 in some areas. Many roads and highways were closed on both sides. 5 trains on their way to the UK from Brussels, Paris, and Disneyland Paris broke down in the tunnel. This isn't the first time a train has broken down in the tunnel during winter. In fact, this has happened pretty much every winter since the tunnel opened. But this was the first time 5 of them broke down at once. While the first train to break was recovered relatively quickly, the other 4 had to be evacuated onto passenger shuttles. And while that was going on, 1,000 cars of passengers were being held on the English side, and 3,000 freight cars were held on the French side. Service was suspended for 3 days, causing a severe disruption that impacted 30,000 passengers, who due to the winter weather had no alternative travel options. So what caused all of these trains to break down? Shocking development. The maintenance procedures were inadequate for the weather and age of the trains. If I had a nickel for every time a maintenance problem caused a mechanical or electrical failure, I would be drowning in nickels. The cars that power the trains require a lot of ventilation due to the heat they output, and at the same time, all of the sensitive components and electronic circuits need to be protected. To prevent the power cars from overheating, they suck in outside air to cool their components. In winter, this means they also suck in some snow. But the tunnel was 25 degrees Celsius and very humid, close to total saturation even, meaning the air had absorbed almost as much water vapor as it can at that temperature. Air has a maximum saturation point, the maximum amount of water vapor it can absorb at a given temperature. The higher the temperature, the more water vapor it can absorb. So when the power car enters the tunnel, the hot, humid air in the tunnel condenses on the cold metal of the train, and the snow that the power car sucked in also melts very rapidly, kind of like how your cold beverage sweats on a summer day. There is also quite a bit of dust in the tunnel air from the rail friction and concrete. The condensation and dust infiltrate the power car systems and cause the electronic and other components to malfunction. Screens had been installed where the outside air enters the power car to mitigate the amount of snow that got in, but it wasn't enough. When the train lost power, it also lost air conditioning and lighting, worsening the situation for the trapped passengers. Following an investigation, Eurostar improved maintenance, operations, and rescue procedures, which appears to have addressed the majority of the issues, but only time will tell. So there you have it, the story of the Chunnel, one of the 7 wonders of the modern world. An engineering marvel that wasn't without its own problems. For photos and sources from this week's episode, head to failurology.ca. There's a link in the show notes. If you're enjoying what you're hearing, please rate, review, and subscribe to Failurology so more people can find it. If you want to chat with me, my Twitter handle is @Failurology. You can email me at thefailurologypodcast@gmail.com, or you can connect with me on LinkedIn. Check out the show notes for links to all of these. Thanks everyone for listening, and tune into the next episode, which remember is in 2 weeks, to hear about the Triangle Shirtwaist Factory fire. A devastating fire that changed the shape of fire safety and engineering forever. But more on that next time. Bye everyone. Talk soon.